Pluto, once considered the ninth planet in our solar system, is a small and enigmatic world that continues to capture the curiosity of astronomers. Though it was reclassified as a dwarf planet due to its unusual orbit, recent alarming statements from renowned astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggest that Pluto may be on a potential collision course with Neptune, a shocking revelation that raises many questions. How could such an event be possible, and what might the consequences be for Earth? Is this an extraordinary astronomical anomaly, or is there more to this impending cosmic impact? Pluto's story is complex and fascinating. As a dwarf planet, it orbits the Sun in a way unlike any other planet in our solar system. A single orbit around the Sun takes Pluto an astonishing 248 years, meaning it hasn't completed even one full orbit since its discovery in 1930. What makes Pluto even more intriguing is its highly eccentric orbit, which is vastly different from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at an angle of 17 degrees to the ecliptic plane, which adds another layer of complexity. Perhaps the most perplexing feature of Pluto's orbit is that it intersects with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we would expect given their positions in the solar system. This naturally leads to the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions between Pluto, Neptune, and other celestial bodies. When astronomers first began studying Pluto's orbit after its discovery, they were puzzled by its unusual shape. While most planets' orbits lie fairly close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentricity. As researchers continued to study its orbital dynamics, they realized that Pluto's orbit crosses Neptune's orbit. The mystery deepened as astronomers wondered how Pluto managed to avoid a collision with Neptune despite their intersecting paths. The key to understanding this lies in a principle of celestial mechanics known as the three-body problem, which involves predicting the motion of three interacting objects, like Pluto, Neptune, and the Sun, and how their gravitational forces affect one another. Despite the seeming chaos of Pluto's orbit, a delicate balance exists between the gravitational influences of Pluto, Neptune, and the Sun. This balance prevents a direct collision between Pluto and Neptune. Two concepts, mean longitude libration and resonance libration, are crucial in maintaining this stability. Mean longitude libration ensures that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune, preventing the two planets from colliding. Additionally, resonance libration refers to the vertical movement of Pluto's orbit. When Pluto approaches Neptune, its orbit is positioned above Neptune's, further reducing the risk of a direct impact. Another important factor in this cosmic dance is a phenomenon called von Zippel-Lindblad-Chi (VLK) swaying, which was named after three scientists who studied the gravitational interactions between multiple celestial bodies. VLK helps explain why Pluto's orbit, though seemingly erratic, remains stable over long periods. It shows that even though Pluto's orbit may appear chaotic, gravitational forces from the Sun, Neptune, and other giant planets help keep its path predictable and prevent major disruptions. Recent computer simulations have confirmed that while Pluto's orbit may experience minor variations, it remains stable over long timescales, ensuring that it doesn't crash into Neptune or deviate too far from its current path. These simulations have also revealed how the giant planets like Neptune, Jupiter, and Saturn play a role in maintaining Pluto's orbital stability. In particular, Jupiter's gravitational pull helps to keep Pluto on a steady course, while Saturn also contributes to the overall stability of the system. This intricate gravitational dance between Pluto, Neptune, and the other giant planets is essential for maintaining the structure and order of the solar system. Without these stabilizing forces, the solar system could become much more chaotic, with planets like Pluto potentially colliding with one another or being ejected from their orbits. Understanding Pluto's orbit is crucial not only for our understanding of this distant world but also for the broader dynamics of our solar system and the behavior of celestial bodies over time. In conclusion, while the idea of a potential collision between Pluto and Neptune may sound alarming, The laws of celestial mechanics and the gravitational forces at play make such an event highly unlikely. The stability of Pluto's orbit, aided by the influence of giant planets like Jupiter and Saturn, ensures that the planet continues its long and winding journey around the Sun, safely avoiding catastrophic collisions for the foreseeable future. This example highlights the fascinating complexity of the solar system and the delicate balance that governs the motion of celestial bodies. The gravitational forces that govern the orbital movements of Pluto and other objects in the Kuiper Belt, a region beyond the outer planets populated by icy bodies and dwarf planets, are influenced not only by external gravitational effects but also by Pluto's intrinsic orbital characteristics. One such characteristic is the inclination of Pluto's orbit, which is tilted by approximately 17 degrees relative to the ecliptic plane, the plane in which Earth and the major planets orbit the Sun. This inclination contributes to the unique orbital behavior of Pluto as it travels around the Sun. Pluto's orbit also intersects with Neptune's orbit at certain intervals in their respective orbital periods. This results in close approaches between the two bodies, despite their different distances from the Sun. However, the gravitational interactions between Pluto and Neptune have, so far, prevented any catastrophic collisions or significant disruptions in their orbits. Astrophysicists and planetary scientists continue to study the orbital mechanics of Pluto and Neptune using advanced computational models and observational data. These studies aim to refine our understanding of the long-term stability of their orbits and predict future interactions between these distant celestial bodies. A key concept in understanding the relationship between Pluto and Neptune is orbital resonance, a phenomenon that occurs when two celestial bodies exert periodic gravitational influences on each other, causing their orbits to synchronize over time. Pluto and Neptune are in a unique 3:2 mean motion resonance. This means that for every 3 orbits Pluto completes around the Sun, Neptune completes roughly 2. This resonance helps maintain the stability of their orbits and minimizes the likelihood of close encounters or collisions. The concept of mean motion resonance is not exclusive to Pluto and Neptune but is also observed in other celestial systems. It illustrates the intricate gravitational interactions that govern the dynamics of planetary orbits and underscores the delicate balance within our solar system. Pluto's orbital stability is further influenced by orbital librations, which are periodic oscillations or variations in its orbit relative to other celestial bodies. These librations help regulate Pluto's orbital inclination and contribute to the overall stability of its orbit over long periods. To study these dynamics, astrophysicists use advanced simulations and computational models to calculate the gravitational interactions between various objects in space and predict their orbital trajectories over millions or even billions of years. These simulations help researchers explore potential outcomes of gravitational interactions between Pluto, Neptune, and other celestial bodies, providing insights into the long-term evolution of the solar system. The study of Pluto's orbit also contributes to the broader field of celestial mechanics and orbital dynamics. The principles and mathematical equations developed to describe Pluto's motion can be applied to understand the orbits of other planets, moons, asteroids, and comets within our solar system and beyond. The discovery of Pluto's moons, Charon, Nix, Hydra, Kerberos, and Styx, has further enriched our understanding of its orbital elements and gravitational interactions. These moons exert gravitational forces on Pluto and contribute to the overall stability of its orbit within the Kuiper Belt. Charon, in particular, has a significant gravitational effect on Pluto due to its proximity and relatively large size ratio compared to other moon-planet systems in the solar system. The gravitational interactions between Pluto and Charon have led to tidal locking, where the same side of each body always faces the other as they orbit their common center of mass. The study of tidal locking and gravitational resonances between Pluto and its moons offers valuable insights into planetary evolution and the processes that shape celestial bodies over billions of years. Pluto's classification as a dwarf planet has sparked debates about the definition and classification of celestial bodies in our solar system and beyond. The International Astronomical Union's decision to reclassify Pluto as a dwarf planet in 2006 triggered discussions among scientists, educators, and the public about the criteria used to define planets and their subclasses. According to the IAU's definition, A celestial body must meet three criteria to be considered a planet. It must orbit the Sun, it must be roughly spherical in shape due to its own gravity, and it must have cleared its orbit of other debris or smaller objects. While Pluto meets the first two criteria, it does not satisfy the third, as it shares its orbit with other objects in the densely populated Kuiper belt. The Kuiper belt is a region beyond Neptune's orbit containing numerous icy bodies, dwarf planets, and other small celestial objects. Pluto shares this region with other Kuiper belt objects, such as Eris and Makemake, which are also classified as dwarf planets due to their size and characteristics. The discovery and study of the Kuiper belt have provided new insights into the diversity and distribution of celestial bodies within our solar system. These icy remnants from the early formation of the solar system offer clues about its origins and evolution over billions of years. The New Horizons mission, launched by NASA in 2006, provided groundbreaking observations and data about Pluto and its moons during its historic flyby in July 2015. The spacecraft's images and measurements revealed detailed information about Pluto's surface features, atmospheric composition, and geological characteristics, further advancing our understanding of this distant world. The intricate dynamics of gravitational forces and orbital mechanics showcase the importance of continuous observation and investigation of celestial phenomena to better understand our position in the universe. Exploring the vastness of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a prime example of this oddity. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly illustrated by Pluto. This means that even minor changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Pluto's status as a cosmic enigma continues to fascinate both astronomers and space enthusiasts. Discovered in 1930 by Clyde Tombaugh, Pluto was initially considered the 10th planet in our solar system. However, its classification underwent a major revision in 2006 when the International Astronomical Union updated the criteria for planet status. Due to its small size and characteristics, Pluto was reclassified as a dwarf planet, sparking debates and discussions about its nature and its place in our solar system. Despite this reclassification, Pluto remains a key subject of study in astronomy, particularly due to its unique orbit and its relationship with Neptune. The discovery of Pluto marked a significant milestone in the history of astronomy. Tombaugh's meticulous observations from the Lowell Observatory in Flagstaff, Arizona, led to the identification of a faint moving object beyond Neptune's orbit. This discovery not only expanded our understanding of the outer solar system but also raised questions about Pluto's true nature. Initially, Pluto's size was overestimated, leading to its original classification as the 10th planet. However, subsequent observations and advancements in astronomical techniques revealed Pluto's modest size, similar to that of some moons in our solar system. This realization sparked debates among astronomers about how to accurately classify Pluto within the hierarchy of celestial bodies. One of Pluto's defining features is its highly elliptical orbit. Unlike the relatively circular orbits of the major planets in our solar system, Pluto's path around the Sun is elongated and tilted. This elongated orbit takes Pluto from approximately 29.7 to 49.3 astronomical units, AU, from the Sun, where an astronomical unit is the average distance between the Earth and the Sun, about 93 million miles or 150 million kilometers. The eccentricity of Pluto's orbit contributes to its complex relationship with Neptune. Despite being much smaller than Neptune and located farther from the Sun, Pluto's orbit occasionally brings it closer to the Sun than Neptune. This unique orbital arrangement raises questions about potential gravitational interactions and collisions between these two distant planets. The orbital periods of Pluto and Neptune further emphasize their unusual cosmic dance. While Pluto takes around 248 Earth years to complete one orbit, Neptune's orbit lasts 165 years. This difference in orbital periods means that Pluto and Neptune occasionally pass near each other, but they never collide due to the gravitational influence of other planets and the mechanics of their orbits. The gravitational relationship between Pluto and Neptune is governed by complex factors, including their masses, distances from the Sun, and orbital speeds. Despite their occasional close encounters, these celestial bodies follow predictable paths due to the principles of celestial mechanics, as explained by Isaac Newton and refined by later scientific advancements. The stability of Pluto's orbit, even with its irregularities and interactions with Neptune, can be attributed to several factors. One key factor is the gravitational influence of larger planets like Jupiter and Saturn. These gas giants exert significant gravitational forces that help stabilize the orbits of smaller bodies like Pluto within the solar system. Mathematical simulations and theoretical models have shown how Jupiter's gravitational pull acts as a stabilizing force, maintaining the relative stability of Pluto's orbit over long timescales. Without Jupiter's influence, Pluto's orbit could become even more erratic, increasing the likelihood of collisions or ejection from the solar system. Saturn's gravitational effect also plays a role in stabilizing Pluto's orbit, though it is less significant than Jupiter's. Together, the combined gravitational forces of these gas giants create a dynamic balance, ensuring the long-term stability of Pluto's orbit despite its eccentric nature.